Hello everyone, I'm Yuan Dai from Fudan University. It is a great honor to present our recent work at ISCA 2026. The title of our paper is LoRA, Towards Improved Applicability of Reconfigurable Architectures for Versatile Nonlinear Functions. Let me start with the motivation. This slide shows what a CGI is. A 2D array of processing elements interconnected through a reconfigurable network. One key feature is word-level reconfiguration, unlike FPGA's bit level. Meanwhile, the compiler statically schedules operations and generates configurations. As shown on the left, by switching configurations, the CGI can execute different tasks. Thus, CGI achieves near ASIC energy efficiency while offering better reconfigurable ability. Compared to FPGAs, its coarse-grained reconfigurable ability leads to higher energy efficiency. CGI typically accelerates compute-intensive loops. A front-end compiler extracts the data flow graph from the loop kernel, and the backend to match the DFG onto the CGI, performing scheduling and generating configurations. By switching configurations, the CGI can execute different tasks. Traditional CGI PEs only support linear operations like addition and multiplication, as nonlinear functions become increasingly common in various applications. Traditional CGIs struggle to support them effectively, limiting their applicability. Several methods exist for nonlinear functions, but each has drawbacks. Cody suffers from linear convergence and high iteration latency, limiting its efficiency for high-precision nonlinear operations. LAT methods lead to exponential memory growth with target precision, making them impractical for high accuracy. Taylor expansions have limited approximation range and require many high-order terms for high accuracy, increasing computational costs. Therefore, piecewise polynomial approximation is more common. The target nonlinear function is split into segments, each approximated by a polynomial. However, applying this to CGI face three challenges. To adjust them and improve CGI support for nonlinear functions, we propose corresponding solutions. First, how to generate the approximating polynomials. We propose a Chebyshev polynomial-based method. Given a target function fx and polynomial degree n, the approximating polynomial f tilde of x is a linear combination of Chebyshev polynomials up to order n. The goal is to find coefficients Ci that minimize the approximation error. After obtaining Ci, we convert the Chebyshev series to a standard polynomials. This slide shows the solving process. First, we sample fx with m points. Since Chebyshev polynomials have the minimax property of -1 to 1, we map the domain to -1 to 1. Then, we build the Chebyshev matrix, where each entry is the value of a Chebyshev polynomial at a sample point. Multiplying this matrix by coefficients Ci gives the approximating polynomial values at the sample points. We solve Ci using least squares, then transform back to the original domain. The above is for a single segment. In practice, piecewise approximation is often needed for better accuracy. Two questions arises: how to determine the break points and how to assign polynomial degrees to each segment, because higher degree may overfit. We develop a full exploration algorithm. We give it the target function, the input range, the mass polynomial order, and the mass number of segments. Then the algorithm automatically searches for a high accuracy approximation. For breaking point selections, we consider the function's algebraic properties and use three search strategies, picking the one with minimal errors. For degree assignment, we first use a curvature-based scheme, higher degree for regions with rapid change. Then we refine with a genetic algorithm. Finally, the algorithm outputs the piecewise segmentations and the polynomial for each segment. Here is the second question: how to compute high-degree polynomials with low hardware overhead? Our solution is logarithmic number system. This slide shows two benefits of LNS. First, by converting to the logarithmic domain, simplifies multiplications, divisions, power into basic operations. This allows us to compute complex, high-degree polynomials use only a few multiplications and additions. Even a terms like x to the 100th power becomes just a multiplications. Second, LNS provides a unified data format. Both fixed point and floating point values are converted into the same LNS format, enabling flexible data format support. Based on LNS, we design a dedicated nonlinear function unit called Xcore. Xcore is a two-input reconfigurable unit supporting 4 operation modes, simplifying complex computations. It is a pipeline design and achieves low latency. We integrate Xcore into LoRA CGI and build a complete SoC. The LoRA CGI includes standard Ps for regular operations, Xcore Ps for nonlinear functions, IOB for bridging computations and scratchpad memory, and GIB for flexible interconnect. It is a parameterized design. User can configure P type for each position. Executing a task on LoRa SoC involves 4 steps. First, load data configuration from external memory by the load controller and DMA controller. Step 2, configure CGI by the CGI controller. Step 3, CGI execute the computation. Step 4, write results back to the external memory by store controller and DMA controller. We also implement a full CGI software toolchain with support for nonlinear functions. The compilation flow is shown in the figure, which includes 5 steps. Step 1, we need to analyze the target nonlinear functions in the loop kernel. Then, we replace the original function with custom functions. Step 3, we need to generate approximation polynomials for the target nonlinear functions. Step 4, we're using a LVM-based front-end compiler to generate the DFG. Step 5, we're using the backend tool to map the DFG to the CGI and generate the CGI calling function. Next, I will introduce the experimental evaluation. We evaluate at multiple levels with various test cases. The unit level baseline includes several nonlinear computation units and Pikachu, the SOTA CGI with Taylor expansion methods. The system level baselines include Pikachu and a STM32H750 MCU. We use Synopsys DC with TSMC 14 nanometers for hardware overhead and VCS simulations for performance and accuracy. First, we did design space exploration for Xcore, mainly looking at the maximum number of segments and the polynomial order. The result shows that if we use more than 6 segments, the accuracy increases significantly. Besides, the polynomial order 6 gives a pretty good trade-off between accuracy and cost. So we picked 3 versions Xcore A, B, C for the next stage evaluation. Then we compare Xcore against other units for accuracy and hardware overhead. There are some key findings. First, Xcore provides higher precision for nonlinear functions. Compared to other general-purpose nonlinear units, Xcore is more flexible, has low latency, and low hardware overhead. We also compare LoRA with Pikachu on end-to-end applications such as DCT, DNN, and LLM. LoRA achieves sufficient accuracy, and thanks to LNS, the computation complexity is reduced significantly. This slide shows the system-level results. Compared to SOTA CGI, LoRA achieved 2.18 times performance and 2.13 times energy efficiency improvement. Compared to the STM32 MCU, LoRA delivers substantial speed-ups. This result demonstrates that LoRA SoC effectively accelerates applications with complex nonlinear functions. We also implement an FPGA prototype of LoRA SoC based on TBR framework. This figure shows the system diagram and the actual prototype. Due to FPGA resource constraints, we built a 4x4 CGI with the configuration shown in the table. The bottom figure shows FPGA resource utilization. We run an image processing application containing nonlinear functions on the FPGA prototype. Comparing CPU execution, LoRa VCS simulation, and FPGA results shows they match perfectly, validating the correctness of LoRa SoC. In summary, to improve the applicability of reconfigurable architectures for nonlinear functions in emerging applications, we propose a Chebyshev polynomial-based approximation algorithm, a lightweight reconfigurable nonlinear unit Xcore that reduces the cost of computing complex operations, and integration of Xcore into the LoRa SoC along with the full-stack software toolchain and FPGA prototype. Finally, the entire LoRa framework is open source. Welcome to download and use it. That concludes my presentations. Thank you.